Horizontal forces. Newton's third law of motion says that if object A exerts a force on object B, then object B exerts a force on object A with the same magnitude and type, but opposite direction. Kinetic friction is a force of friction between two surfaces that are moving relative to each other. Static friction is the force of friction between two surfaces that prevent slipping and or sliding. Traction is a frictional force that allows for motion. Even though you may have memorized Newton's third law in a catchier way, it's going to be a lot more useful if you memorize this really long sentence. Okay? If object A exerts a force on object B, then object B will exert a force on object A with the same magnitude and type, but opposite directions. What that means, if we have a box on top of another box, the red box, or the top box, is going to push down with mg, and the orange box is going to push up with a normal force. If I analyze the forces acting on the orange box, there's a weight force and a normal force from the red force on the orange box, and then there is also that normal force acting upwards. So this normal force upwards acting on the red box and this normal force acting downwards acting on the orange box, these are what are called force pairs. So these two forces are the same magnitude, same type, and opposite directions. Because the red box pushes on the orange box pushes on the red box. Kinetic friction, when two surfaces are in motion relative to each other, kinetic friction acts in the direction opposite of the slipping that is happening. Looking at our forces acting, we have the weight force going down, the normal force going up, tension force to the right, and a frictional force to the left. That frictional force is not equal to the tension force, so clearly I can see that this box is accelerating to the right. Because it's accelerating to the right, it doesn't necessarily mean I know the direction of the velocity. It may be moving to the left, but is slowing down, or we may be moving to the right and speeding up. All the net force does is predict the direction of acceleration, not the direction of velocity. To deal with kinetic friction problems, we're going to identify that there's forces acting. So if you see something like rough surface or frictional force or anything like that, or a coefficient of friction being given in the problem, then that means there's going to be forces involved. Draw a free body diagram for each object in the system, create a Newton's second law equation, stuff that makes it go minus stuff holding it back equals mass times acceleration. Solve for whatever we need. Remember that your frictional force equation equals mu k times Fn. So we can plug that in and solve for tension if we want. We can solve for the coefficient of kinetic friction if we like. Whatever it is we are asked to do, we can do. Remember that x and y directions have to be treated completely separately from one another. Static friction. Static frictional force acts when an object is being pushed or pulled, but does not move relative to the surface it is on. So same force is acting, but this time my frictional force is equal to my tension force, so I'm in equilibrium in the x direction. So my net force in the x direction is going to be the stuff that makes it go minus stuff holding it back equals F equals 0 because it's not moving. So that means my frictional force equals my tension force, which is useful. For this equation, frictional force, remember this is in that absolute value and it has the less than or equal to sign, absolute value, mu times Fn. What this means is the maximum amount of frictional force that needs to be overcome can be solved using this equation. Ff equals mu times Fn. Once the tension force continues to increase and eventually becomes large enough that it overcomes the frictional force, then we go back to kinetic friction. So while the object's not moving, we're using static friction. Then when it does start sliding or slipping, then we're going to use kinetic friction. Friction is needed to help motion. For you, when you walk on the earth, we have your shoe and you push down into the back on the earth. You have a weight force acting down. You have a normal force acting up that is equal and opposite to that weight force, which is not a reactionary pair. It is not a Newton's third law equation. To figure out the Newton's third law, and to figure out the action-reaction, the action is you pushing down with your foot. The reaction would be the earth being pulled up by you. And the normal force. So your normal force of you pushing down on the earth, or the earth pushing up on you, you are also pushing down on the earth with that same normal force. You're pushing backwards on the earth and you move forward. The reason for that is the earth is exerting a frictional force on you to the right because you are exerting a frictional force on the earth to the left. So when you push down on the earth, or when you push back on the earth pushes forward on you. If you're able to increase your amount of friction, then you're going to increase the amount of friction that the earth pushes back on you. This is how runners increase their speed. Special running shoes allow for the design of the foot to come more in contact so a greater force can be applied so they can increase their speed. Let's say we have a wheel on ice, like that's part of a car. If the ice is frictionless, then that car is never going to go anywhere. So instead, there has to be a frictional force between the tire and the ice. And if you think about this microscopically, all surfaces have these ridges to them if you were to zoom in on it. So you have the ridges of the tire, and then you'll have the ridges of the road. And those ridges are in contact with each other, and it's really hard to overcome them. The harder it is to overcome them, the greater your coefficient of greater the coefficient of static friction is. It means there's more friction. Once you start overcoming them, then you start sliding for a normal object. A wheel is a special case because a wheel ideally is not slipping or sliding. Instead, little points of the tire are coming into contact with the road one point at a time, and they're not sliding relative to each other. So for any wheel that is rolling without slipping, this is a static frictional situation. And you have to have friction in order to cause this movement. This is called traction. It's why your tires have tread on them, to allow for greater grip. Let's look at an example. In the figure below, the block mass M has come to rest some location to the right of the spring's equilibrium position. The spring has a spring constant K, and the coefficients of kinetic and static friction between the block and the surface are mu K and mu S, respectively. Derive an expression for the maximum displacement possible for the block that will allow the block to still remain at rest. Explain your answer in terms of capital M, K, mu S, and physical constants as appropriate. So we're dealing with a spring force and friction, because the problem keeps mentioning friction. These are all forces. So first thing we need to do when dealing with a force problem after we've identified it as such is draw that free body diagram. We have weight and the normal force in the vertical direction, and in the horizontal direction we have the spring force trying to pull this block back towards that rest length, that equilibrium position, and we have a frictional force that's preventing that from happening. At some point, if you pull too far, then that spring force is going to grow. So there is a maximum length that this situation can happen, and that's what we're trying to find here. We're going to call the maximum length, or the maximum displacement, x max. So next step after drawing our free body diagram, stuff that makes it go minus stuff holding it back equals mass times acceleration. We're only looking in the x direction here because That's all that really matters for now. Our equation for our spring force is K times X minus the equation for the frictional force, mu S times Fn. And that equals 0 because this object is at rest. We can add the frictional force to the right side, so we get Kx equals mu S times Fn. And then we can just solve for x max, which gives us mu S times Fn divided by K. Is that it? Let's check. Express your answers in terms of m, k, mu s, and physical constants. Mu s, that's allowed. Fn, that's not listed, so that's not in. So we need to figure out what is our normal force. Looking at our free body diagram, it's pretty obvious what our normal force is equal to. It's equal to the weight force. Capital M times G. G is a physical constant, so we're allowed to use that. Next up, I want to give you an example that is going to give us a preview of the next lesson, and that's solving for half of an Atwood's machine. So if we have this situation where we have half of an Atwood's machine, half of an Atwood's machine would be a table, a box on the table, a pulley, an ideal rope attached to another mass. We'll call mass on the table M1, we'll call mass on the table M2. We can figure out the acceleration for this situation even if there is frictional force involved. The way that we're going to do this is we're going to treat the x and y directions completely independent of each other. So we'll have a net force in the x direction, and we'll have a net force in the y direction. And you just need to draw your free body diagrams to see what is happening. So we have our weight force and we have a normal force, m1g, and then we have a frictional force and a tension force. If this system is accelerating, then we know that frictional force is going to be our kinetic friction. For mass 2, this is a lot easier. We have the tension force going up and the weight force going down. If we treat the tension force as an internal force to the system, then the tension's just going to cancel out, and we could just figure out stuff that makes it go minus stuff holding it back. The stuff that's going to make it go is going to be m2g, and the stuff holding it back is going to be our frictional force, equals mass times acceleration. That's a total mass of the system. So m2g, stuff that makes it go, minus our frictional force, mu times Fn, and Fn is going to be m1g, equals m1 plus m2 times a. Now, dividing by m1 plus m2, we get our acceleration. m2g minus mu m1g, and you can factor out the common g's there. Or don't. Either way, it's still the same true answer. So that's a sneak peek. Previously, when we keep our x's and y's separately, we reference that when the forces are at an angle. But because we're treating this thing as a system, our tensions cancel out. We don't have to do that. We can take this shortcut of just seeing what is actually causing this system to accelerate. Next steps. You can never solve too many problems with these. There's your AI prompt. Ask each other, ask me, and keep asking until you get it.